All right. Okay, so just for those who are going to view the video, I started recording a little late. I just introduced a very simple query and talked about how it translates into a relational model, and the database eventually translates those relational models into opcodes that are more optimal for execution. And now we are talking about all the primitives that it takes to translate a SQL statement into a relational representation. So in this case, actually, if you look at the primitives, scan is special. The reason why it is special is because it is the only primitive that does not take a result as an input. It takes a table name as an input and then scans the table. If you look at all the other primitives, they operate on existing results. So once the scan takes a table as an input, produces a result, and then the other primitives come in and process that result and convert it to different forms, mostly into another result. Like a filter takes one result, produces another result. What that means is that these other 8 primitives are completely interchangeable. And they are completely combinable. You can take a join and pass it to a filter. You can take a select and pass it to an aggregate. You can take a sort and give it to a limit. We'll go through how that gets represented in a select statement. But if you go back to the original query, you will see that most of these primitives are actually very straightforward. A filter is basically your where clause. A select is basically your select expression. Sort and limit are pretty much self-explanatory. Merge is basically your union. So there's almost a one-to-one map between an SQL construct and these relational operators. There are a few exceptions. Aggregate is one exception because aggregate is represented as partially in the select expression and partially in the group by. So there is some complication there. Otherwise, it's mostly one-to-one, and we are going to actually use that one-to-oneness in our design, and I'll cover that later. And the other thing that you should think about is a SQL is actually very, very simple as long as you don't do joins or subqueries. It's actually, you can probably implement a SQL engine that doesn't do joins or subqueries in maybe 500 lines of code. I don't know, but very, very few lines of code are needed to do a simple SQL engine. But as soon as you introduce joins and subqueries, it's a total explosion of complexity. Not only because of the fact that they add that complexity, it's also because you need, the optimizer has to do a lot more work to do the right thing when you have subqueries and joins. So that's the reason why those things are very difficult. There is another axis that I did not include, but which actually is very significant, which is it doesn't end with these relational primitives. We also have to deal with scalar operations. When you say select a plus 1, you have to be able to do those operations also. And those operations, when they combine with these relational primitives, and when you talk about joins and subqueries, it becomes pretty much what you call a combinatorially unsolvable problem. Practically, you have to use heuristics to figure out optimizations for your query because there's just too many combinations to analyze otherwise. So, typically database engines, what they do is they actually introduce new primitives that are basically combinations of existing primitives or different ways of doing the same primitive. Like a scan could be an index scan, which means that it scans only a range of rows. A join can be using different join algorithms depending on how the data is organized. BNL, I think, is called block nested loop join, for example, which is what MySQL does. MySQL doesn't do hash joins. Like sorting, it can do a file sort, or it can do an in-memory sort, or there's merge sort, so many algorithms. And the engine has to decide what is the most appropriate based on the input query and what it understands about the data. So this we covered this a little earlier. So basically, there are 4 steps to what a database engine does. It takes the SQL as input, runs it through a parser, and builds the AST. And the AST goes through a plan builder that converts it into actual relational operations. And the first set of relational operations that are built are typically not optimized. And then the optimizer goes in and applies, changes those operators into something that can be more efficiently organized. And for something like MySQL, the most common one is look at the where clause and see what indexes match that where clause. And let's see if we can do a primary key based scan or a secondary index scan, and then use that result to do the stuff. Everything else is mostly work that MySQL has to do. It may actually sequence things differently based on, like, for example, if you have a constraint in a having clause, it may say, well, I don't want to wait till I do the select. It looks like I can do this upfront and reduce my result size in the beginning itself, so I don't have to carry that much memory. So those kinds of optimizations that the engine usually does. The other thing that a relational engine needs to have is basically a symbol table. Symbol table is a way to validate the correctness of your query. Because if your query has references a column of a table, it needs to validate to see, does that table really have that column? If it uses a table, it needs to validate that the table exists. And there are scoping rules, because if you have a query and then there is a subquery, there are rules, and the subquery uses a symbol that is present both inside the subquery as well as outside. Yeah, there are some rules about which symbol it actually references. And the other thing that it has to do is once a SQL has select expressions, those actually create new symbols that can be referenced in other parts of the query, like in the group by clause and order by clause. So when that happens, the symbol table tracks those new symbols that get created. And obviously, validation. And finally, the symbol table is used for optimizations because it tells you that this column has an index, this is the cardinality. So all that information actually is driven through the symbol table. So it's a pretty critical part of an engine design that you need to have a symbol table. So what makes joins and subqueries complex is basically that in the traditional sense, a join is basically a cross product of 2 tables. That's how relational theory describes a join as. And cross product is never practical, which means that as soon as you see a join, the relational operator that you generate for it is useless, unless you actually really want to do a cross product. So the first thing that MySQL tries to do is the most common case is that there is a how do you even do a cross product, right? You have to, and the most common algorithm is a nested loop join, where you start with the first row and use the result of that row to the first table. You decide which table you want to start with first. And then you start iterating on the rows of the table, and as each row comes in, you go to the other table and run something like a subquery, which is basically use the input, the first row as input to get the row from the other table, and then join the tables and then return the results. So that's actually the most common case, which MySQL also does. I think MySQL has a couple of other join algorithms, but they are essentially nested loop joins. It's only how it groups them and how it. I think it fetches a bunch of rows and then fetches another bunch and then does a join. But it's essentially an optimization on the basic nested loop join. Oracle has something called the hash join, which is actually pretty cool. If one of the tables is small, it can hash that table in memory and then do the join very efficiently. That actually is very efficient in some cases. More than joins, subqueries are the real nightmare when it comes to analyzing SQL. So if you, subquery itself can be either a simple subquery or a correlated one. If you see in this example, the first query is a simple subquery, right? Select a column from the table where ID is, and then you go to the subquery. So you execute that subquery first, get the results from the table, and then apply the values as if they were specified in an in clause. So the first query. Can someone tell me what the second query does?
It basically fetches the name in the subquery. It fetches the name column from table T1, uses the output of that and feeds in as the input in the where condition for table T2.
But is that the case? Why not the other way around? Right? It could be select from T1.
Mm-hmm.
And then use that value to select from T2, but use the name as constraint. So that's another way. Actually, the question was, what does this query mean? Actually, it was a trick question. The answer is we don't care. We only care about what needs to be done to return the results of this query. We don't really need to understand what the user is trying to do. I used to get into this mode where anytime I saw a query with a subquery, I used to try and understand what the query is trying to achieve. But when you're designing an engine, you don't really care what the query is trying to achieve. You only care about what it needs to do to return the results. Only the user cares what the query needs to achieve. So in this case, actually, the relational way to represent this is kind of like a join. Basically, you run the first query and then use the result of the first query to drive the secondary query, and then apply a filter on the result of the second query, again back into the result of the first query to produce, to decide whether the row needs to be produced or not. So this, so we don't that rule actually works for the first query also, even though it would be very, very inefficient. Because in the case of the first query, the subquery always results in the same results. It always produces the same results, but technically speaking, you could, for each row, you could run the subquery and then apply the in clause. So from a correctness perspective, what you do for both queries is the same. But from an optimization perspective, you do something very different with the first query compared to the second one. And the big problem with subqueries is that it actually has multiple forms. A subquery can be used as a simple scalar value, which means that where you can say, select something from a table where t1.id equal to select something. Or it can be used as a column tuple, like the example that is there. Or it can be used as a row. Or it can be used as rows of columns. And at the end, it can actually be used as a table itself. You can actually select from a subquery. Because of all these forms, basically what this says is that a subquery can pretty much appear anywhere in your current query. And the reason why this is complicated is because you are parsing and analyzing a query, and halfway through you encounter a subquery. what do you do now? You are not fully done analyzing your current query. Now you set that current query aside. You go inside the subquery, and then you have to analyze the subquery separately. But then you also at the same time have to figure out how to optimize the thing, right? Like in one case, in the first case, you analyze the subquery, you come up with a completely different decision than you would do with the second query. How do you reconcile that while you are still analyzing one query, where we are halfway done analyzing one query, and you are analyzing another query, and the problem kind of becomes recursively more complex because the subquery itself could have another subquery. So then what happens, right? What happens? Do you set that subquery aside? So there's a lot of special cases that can arise due to the fact that there is a subquery. So it's kind of a big headache, and I will show why that is painful and how we overcame that in V3. But the simple way to look at a subquery is it's like a join. Basically, the mechanism of executing a subquery is like a join, which means that you run the main query, get the results, and use that result as input to the subquery. The only difference is that in the case of a join, the rows are joined one left to right, whereas in a subquery, usually the result is used to apply an additional filter or perform a different operation. So that's the only difference. And in a way, a subquery is likely a superset of what a join can do. I think any join can be represented as a subquery. Don't quote me on that, but I think it's possible. All right, so this is typically what an SQL engine looks like. When a query comes in, a machine has CPU, RAM, and in storage it has indexes and tables. And when the engine starts up, it loads up the schema. And when a query comes in, it looks at the schema and then makes a decision about what to do about that query. And then it performs index scans, and those constraints and pointers are used to scan the table. And the result is then returned back to the application. The RAM is used for both locking and optimizations because it can cache some of the results, and it can check the RAM for pre-existing results. If it's already there, then it doesn't have to scan the tables and stuff. And if you look at Vitess, the architecture looks the same, except that the VTGate is kind of like our CPU, but it uses a vSchema. The lookup table is like an index, and the database is basically sharded. We actually plan to introduce a row cache in the future. When that comes, it will actually complete the view of Vitess as a distributed SQL engine. However, there are some differences, which is in the next slide, but I can point it out here. One big difference is that each of these items is a full-fledged database, which means that these boxes can do a lot more than what an index here can do. Here, all you can do is an index scan, whereas here you can do a lot more stuff. The other big difference is that VTGates are far away from these boxes. It's a network round trip away, whereas here they are all within the same box. So when you make decisions, you have to take these two factors into consideration, which the fact that these are more intelligent and that the distance between these two is higher, which is basically what the next slide talks about. The storage node full database, higher round trip cost. There are a few more differences, which is the fact that the data is sharded is something that we have to take into account. That means that we have to know when the rows are together in one shard and when they are not. And rows that are together in one shard will have special efficiency, whereas if they are distributed, then there's more work to be done. That work is actually similar to what MySQL does with partition tables, but it's still different because MySQL can afford the CPU is being closed to the disk still allows for some operations to be local, right? Whereas in our case, we are far away from the database. So not all those optimizations apply to us. And the Windex design is also different. And the biggest difference is the fact that we have a pluggable Windex, which I think is an advantage, which means that you can actually have different types of indexing options depending on how your data is distributed. So these differences are going to affect how we are going to design our V3. Basically, we cannot just take code from MySQL and make it work for V3. That's or take code from SQLite or whatever, any SQL engine, mainly because of those differences. And if you look at a relational engine, the biggest difference is that if you look at it from a NoSQL perspective, right? VTGate is basically a query router. You send a query, it has to figure out where that query has to go. That's one way to look at it. If you come from a NoSQL approach. So from that perspective, VTGate or Vitess is just a router. But from the other perspective, it is also a complete engine because it has to be able to handle queries of any complexity. And the conclusion is it is both. And it is actually both. And it's also a hybrid because sometimes it has to do some routing and some engine work. And how to balance the two is the challenge that V3 tries to solve. So in the case of a relational engine, the design is super simple. The approach is simple because you go only one way. You start with an SQL, go to AST, go to relational opcodes, and then DB opcodes, and then you're done. But if we are now in the V3 world and the VTGate world, we have to be able to come back from our whatever representation that we have back to SQL because that's what the underlying engine understands. Right? If I create opcodes, I cannot give those opcodes to MySQL and say execute them. I have to translate them into SQL and then give them back. And it would be beneficial if, in such cases, the original parts of the SQL were used because that will make it more readable and understandable. So that's one of the design constraints that we added is that the query, if it is actually a pass-through query, should retain its original form. Okay, so we now have a new approach, which we call the hybrid approach, which is based on the fact that once you from SQL you can go to AST, and from AST you can easily go back to SQL, which is actually something that we do all the time. VT tablet actually doesn't actually execute your original query ever. It actually builds an AST and then generates an SQL based on that AST, and that's the query that it executes. That is actually, we did that just to prove ourselves a point and to actually exercise that code path for every query that comes to make it more robust. We could have actually said, well, we'll analyze the query, but we'll use the original query as just as pass-through, but then that code would not get exercised as often. But instead, we made the conscious decision that we will always rewrite your query so that that code path gets used and is robust, right? Which basically allows us to trust that when you go from an SQL to an AST and then the AST back to SQL, we can trust the SQL that we generate. So now we are going to use that confidence to play around with AST elements. So what we are going to instead do is when we generate opcodes, we are now going to not generate relational opcodes. We are going to generate hybrid opcodes, which contains AST elements. So basically, if we decide when we are analyzing our query and we are saying that, okay, this part does not need to be handled by VTGate, it can be sent to a MySQL, then we say, okay, we'll save away that AST element inside this opcode and then not do anything with it. And we kind of push down those AST items, data structure items into the opcodes. And then at the end, when we finally generate the final code, we just say AST convert yourself to SQL, and that SQL can be sent to the underlying VT tablet. So it gives rise to some confusing parts of the code, but eventually it is beneficial because in most cases, VTGate just only routes your query to one of the VT tablets. So it's actually very beneficial to do it this way. Any questions so far? No questions? Okay.
Would it be possible for you to, I know we're going to be talking, this is like mostly the theory and we're going to talk about the implementation later, but can you just give like a quick example of the last slide in terms of an actual Vitess operation?
Let me see. That's actually coming up ahead.
Okay.
Let me see if I can. I can run a quick animation of what is there to come.
Sure.
And let's see. I'll show you a simple one. So here's an animation. We'll go through this. This may actually take an entire session.
Okay.
Actually, this is not a good one. Let's start with this one. So here is an AST on the left. It's basically a select statement that is now represented as data structure. And we are going to build the plan for it. And this is actually a join that VTGate is going to perform. So it has built two routes, one for table A and one for table B. And then if you go to the animation, it says it built the join node, push the A.n equal to B.n to this AST, change the route plan, push the other where clause to this AST, change the route plan, push the select expressions into this AST, and do this, and there you go. Oops. So this is kind of how the hybrid plan works. So basically, we start with the AST and then push these nodes into other AST nodes and build our SQL underneath. Does that make sense?
Yep. Thank you.
So we'll come back to this. Hopefully, I will spend less time explaining that part because that usually when I explain that slide, it takes an entire session. Hopefully, if we have gone through this upfront, I'm hoping that we won't have to spend as much time there. So we have to decide what are our VTGate primitives at this point. And we are going to say that the most important primitive that VTGate is going to build is the route primitive, which is the ability to send a query to one database. And one database could be an unsharded database, or it could be a single shard of a sharded database. So that's basically what a route does. And there is a special case of a route, which we call the scatter route, which basically says, send this query to all shards of a database. And when the results come, just combine them and send them back to the client in any order. It's basically, this happens if you are doing a full table scan of all, or if you want all rows of a database. Or if you have a where clause that has no sharding key, which means that the rows could be found on any shard. So typically, that's when a scatter route happens. So this is the most core primitive of V3, just the ability to send a query to another tablet server. And our V3 strategy is basically when we get a query as input, we have to figure out if all the rows that are needed to satisfy that query are in a single database. If we can figure that out, if we figure out that, okay, all the rows that are needed to satisfy this query are only in one database or only in one shard, then we can send that database into that query to that database, and whatever results it returns, we can just return it back to the client and our job is done. But if in our analysis, so basically we have to have the ability to analyze that and come to that conclusion. So that's problem number one. We have to be able to look at a query and say, okay, this query needs only rows from this shard or from this unsharded database. The next problem we have to solve is if we conclude that a query needs rows beyond one shard or one database, can we split the query into parts where each part can be sourced from a single shard or a single database? And if we do the split, can we combine the result meaningfully when the results start coming in? Can we combine the results to return whatever comes out of those back to the application? So that is problem number two. And if so, what are those operations, right? Is it a join? Is it a aggregation? Is it a merge? So that's the kind of question that VTGate has to solve, which is basically the thing. What is the leftover work needed once we decide to split a query into parts? What is the leftover work needed to stitch the results together to satisfy what the application originally requested? So that's basically the high-level strategy for V3. So the priority is always, can I send this entire query to one database? If so, then my job is done. So far, so good?
So far, so good.
Okay. So, so we are going to introduce the first primitive for VTGate. First work that VTGate has to do in terms of stitching the results, which is the join primitive. So if I get a query and it's a join, and unfortunately the join happens in two different shards, which means that the left table rows are in one shard, and the right table rows are in a different shard, which means that I have to do run the query on the left, run the query on the right, and then stitch the results together. That is what is called as a join primitive, and we have implemented that in V3. And there are two join primitives. One is a simple join, and the other one is a left join. The two are different for various reasons. They are different from the perspective of optimization and from the perspective of what work you can outsource. Like for example, you cannot push down a where clause if there is a left join. So we'll come to some of those. I don't know if we'll be able to cover those details, but there are some constraints. Basically, a join and a left join are actually relationally different operations, and what you can, the transitivity rules are actually different. That's the reason why they are different. But when operationally they are very similar, which means that you take the row from the left-hand side, run the query on the right-hand side. The only difference between a join and a left join otherwise is that if there is no result, you just put nulls and then return the result. So from an execution perspective, they are very similar, but from optimizations and analysis perspective, they are actually very different. And that's it. VTGate is, at this point, has only these two primitives, nothing else. We eventually want to support the other 9 primitives and the arithmetic ones, but we'll get there over time. But you'll be surprised at how far we can go with just these 2 primitives, route and join. And I will go through some use cases here.
What would adding support for those other primitives look like in terms of like, what would that enable in VTGate, considering we can already do, like you said, those 2 already get us most of the things?
Yes. So the best way to look at it is most typical OLTP queries, where if you are running a query to basically serve a web page, typically those queries we should be able to support with just these 2 primitives. But if you're going into the data analysis world, where you are actually looking for deeper relationships that don't exist originally in the schema, those, in order to satisfy such queries, you would need to do a lot more work after you fetch the rows from the original database.
Gotcha. So you're talking about the case of having a sharded or a sharded key space, being able to do an aggregation across them. Obviously.
Yeah, like big data queries, I would say, like where you're doing complex group by that are not grouping by the sharding key. Group by, I want to do a gender analysis of our customer base and age analysis and that kind of stuff.
Okay.
Those would most likely not work for VTGate. And the idea is that if you have to do that type of analysis, you are also likely to require a large amount of caching, which means that you may have to sort 1 million rows, for example, right? So if you have to do that kind of analysis, you may actually benefit more from a MapReduce style setup than the current VTGate setup.
Yep, makes sense.
And we have actually brainstormed the idea, and apparently it's not the first time this idea has been floated, which is basically if you give a complex query, there are apparently algorithms that can change it into a MapReduce job.
Hive, for instance.
Oh, is that what Hive does?
I believe so. It can turn it into a multi-stage MapReduce.
Yeah. So we want to do that, except we still have our hands full with some core features. So once we've done all that, I definitely am interested in looking at doing that.
Cool.
We do have a huge advantage over any NoSQL based system, is that we can push down a lot of complex work into the MySQL part, which NoSQL engines cannot do. If you take a system like Hive, it pretty much has to fetch all the rows from the database and then do all the work after fetching. Whereas if we can apply a where clause right at source, we can do that with MySQL.
Yep.
So we definitely have that advantage, if and when we get to the point where we'll support these things. Oh, and by the way, these are actually in use at YouTube. There is a lot of people running MapReduces directly on our MySQL engine, and so that works very well. So we know that it works, except that we just haven't built what is needed for people outside to use it.
Gotcha. Cool.
Sorry, I had another question about that last slide.
Yes.
So, and I also, it's also kind of coming from maybe something that you didn't just say, but is in that V3 high-level design document, or maybe the V-index design document. You were just saying though, like for a join, and yeah, this goes back to this like block nested join. If it's across shards or across databases or something, you're going to pull the rows out from one, let's say shard, and then for each row, you're going to like pull rows from the other.
Correct.
Okay, so if you're MySQL and you're doing this just, down a layer, where you're talking about indexes and tables instead of shards and databases, you're talking about round trips to disk and maybe row cache and stuff like that. For VTGate, however, I mean, if you're going to loop over a row set from one side of the join, and then for each row,
Yes.
I mean, that's another network round trip.
Yep.
Okay.
Very, very expensive.
Yeah. So how is this like not a complete non-starter from the get-go? Like I read that and I said, that has to have been written wrong. There's no way that could possibly work ever. if that were blackboarded, we would like erase it immediately because obviously.
Yeah. So basically, there's two answers. The first one is that feature is not to be abused. Use it only when you have to really do it.
Which means that actually, like, the cost of that needs to be like surfaced to our users, right? So here,
yes,
we've got like
so basically
100 or 200 people writing SQL queries, and
right. You definitely have to tell them that joins will not work like before. Yeah. Okay. And cross-shard joins. If V3 is very smart about joins that can be done locally.
Yes.
So when it makes a decision that this is a cross-shard join, it means that it's impossible for that query to be done locally.
Yeah.
So the typical use case is so the idea is that you are fetching a handful of rows, even if you're doing joins, which means that you're probably doing very trivial operations where you got one row and you fetch a couple of other rows from somewhere else. So like I said, the idea is that you're building a query that is that's going to serve a web page. So you're not doing complex data analysis here. You're like, if you're like a use case that was presented by Flipkart is we have orders and we have items, shipment items. And for whatever reason, the way they've designed it, they don't necessarily exist in the same shard. So basically what you do is you fetch an order and then get me all the items for this order. So there may be 10 items for that order, which may actually be one round trip to one shard or a couple of other shards, right? And those would, and those should happen in parallel, if I remember right. So you fetch an order, fetch the items associated to that order, and then return the result. So that is practical. So those are the kinds of use cases that this was built to support.
I see.
However, this is only our first version. There is an easy optimization that we can make that I haven't done yet, which is if the join is by a unique index, then you can do block fetches, which means that you fetch 10 rows from the original table, and just basically the second query fetches all the rows that would satisfy any of these 10 rows. Just send an in clause in, and then fetch all the rows and then join them at the VTGate level. So basically, it's basically our version of block nested loop join. The same thing that MySQL does.
Yeah.
But that still restricts to the allocated memory on the VTGates. You still cannot go beyond.
Yes. And it goes back to the point that these are OLTP queries.
Right.
So you're not supposed to fetch 50,000 rows. And actually, there is a limit on VTGate that you can specify, saying that don't fetch more than 20,000 rows per query or something like that I added just for this particular case.
Sorry, could you say that again? Sugu, are you saying that you have like limits that are like query type sensitive? So it knows like, oh, this is going to be a cross shard thing, so we're going to limit row fetch differently than non-sharded?
Yeah, I don't remember anymore, but I believe that's the case.
Okay, because that seems like exactly the kind of thing that we would want to make sure is in place, just so like, oh, put a join in here and then.
Yeah, like VT tablet by itself limits, like the default limit is 10,000 rows. Then I realized that if you are doing joins, that could multiply, right? 10,000 into 10,000, you could fetch 1 million rows. even though each VT tablet only returned 10,000 rows each time. So when we realized that, I added that constraint saying that, well, yes, VT tablet has its limit, but VTGate should also have its own limit because things can multiply.
All right. Yeah. Thanks.
Yeah. And then there is also the streaming support. You can actually stream a join. And that also works, but it'll probably not practical. But the functionality exists because it was trivial to implement, so I implemented it. It probably doesn't make sense to the way it works now, but that's one place where a block join would be actually useful and beneficial.
Yeah, it seems like the loophole that was created that can actually like take the whole system down. Well, yeah. We didn't want to put the foot gun in here, but actually it was easy, so we just made it happen. But be careful. No, it's useful, but yeah, we need some way to ensure that people understand the cost of the queries that they're writing.
Yeah. I think that's that is something that unfortunately that you have to that every user has to. It's a growing phase that every user has to go through. Is that as soon as you distribute your data, you have to know that data is distributed, and there are some things that are just going to not work, pretty much, or not work very well at all.
Yeah, definitely. I imagine that, like, so I've said before at HubSpot, we don't really have any sharded databases at this point. And so by the time we go to like start sharding some of these, I imagine it'll be on a case-by-case basis, work with these people to be like, okay, your database is now sharded. Watch out with these.
Yes, yeah. Like in the early 2000s, there was this concept called location transparency, which was basically a pipe dream that database people had, saying that, oh, we distribute the data completely transparently to you, and you won't know, and it'll just scale indefinitely, and nothing will change for you. That was basically a lie. So something will change, some things will work better than other things. We basically have to choose what should work well for us and optimize for that, and then pay the price for everything else.
I think it would be interesting potentially to talk to you at like either offline or at another juncture about what you guys ran into when you first started enabling joins in Vitess, or if that was, I mean, YouTube's at a larger scale, so it's possible it was always the case, or like how you trained people who were just able to submit queries against Vitess.
I can answer that question right now. The truth of the matter is that we did not. V3 is actually not something that YouTube uses yet.
Okay.
But V3 was built inspired by how YouTube uses Vitess.
Gotcha.
So the way we came to this result is when so the V2 API is super primitive, right? All it does is the application gives you a query and says which shard it has to run on.
Mm-hmm.
So what people did to do joins is basically they do their joins in the application level.
Mm-hmm. Okay.
So they fetch a user row and then look at it and say, okay, I need video rows for this user. And then they send a query and say, now fetch me the video rows for this user. Mm-hmm. And then they say, oh, okay, this is some movie or something, fetch additional information about that. Or this video has restrictions, fetch me. So these joins actually could have been done at the MySQL level. But because they sometimes are in different shards, they actually fetch the rows and then send the query back. So these are actually nested loops that the applications perform today at YouTube to fetch, to perform these joins that would have otherwise been done as a single query. And then we thought, well, why not support it in V3? It is necessary work that the application is going to do anyway. But at least if V3 does it, we'll be a lot more efficient than if the app did it.
The neat thing about your current setup at YouTube then is actually that the cost is obvious to the user.
Correct. It is very well understood by the user. Whereas if you just let this query through into V3, then it is hidden.
Mm-hmm.
Yeah. So that's the caveat of making things transparent or opaque.
Yeah. If you make it invisible, then haha, it's invisible.
Yes. Yeah.
I think the advantage to that would be that you can pretty much shard at whatever scale you could. That way, you really don't have to worry about joins inside one shard if you're not joining data at all.
Yeah. 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 So for most use case, so far at least the users that are here, HubSpot is probably you're probably the pioneer in this, where you are going into an area where your users don't know that the application is going to be sharded. But like Stitch Labs, for example, they came from a sharding background, so they understood these things right from the beginning.
Yep.
So I guess it's a cultural thing.
Yeah, I mean,
but we did. It is painful because, and the pain cannot be avoided. You just have to plan that this pain exists, and you have to work on educating your engineers about this pain.
Yep.
Basically, they have to now know that the two things that they have to know is, one is some operations are not going to be as fast as before, and the other one is your ACID rules have now been relaxed. Your data may not be as consistent as it was before.
Only in the case of a sharded database.
Some data are more consistent than others.
Yes, yes. So you have to know that, yes, you get consistency, but they are localized. So you have to know where you want it and where you don't.
Great.
And those who try to hide that from the users and provide the same consistency, all those systems have failed. And the simple answer to that is because of the CAP theorem. The CAP theorem basically says that you can either give strong guarantee or strong performance, but you can't have both in a distributed system. So unless you relax some guarantees, your system is not going to perform as well as it can.
Yep, definitely. Yeah, we do run a bunch of distributed databases, just not MySQL distributed. MySQL has been saved primarily, like at HubSpot, we've had this rule where it's like, if your data is relational, put it in MySQL with an asterisk. If it's more than like 100 gigabytes, put it in HBase, even if it doesn't make sense to go there. And so that's what we're trying to like remedy.
Yeah, so that's the reason. I like if you ask me, that is actually the reason why relational databases are not as popular today as they could have been, is because I think users would have been willing to work with a relational database that was not 100% ACID.
Mm-hmm.
But relational databases were afraid to come out of that commitment and say, okay, we'll relax some of these ACID rules for the sake of scalability. I think if they had relaxed those rules early on, we would see a lot more relational usage today than we see as of now.
A little bit worse than that, most relational databases that tried to go distributed actually even still claim to have some kind of ACID guarantees until Kyle Kingsbury came along and kind of shot them all in the head.
Yeah. So hopefully Vitess will reverse that trend. Maybe Vitess will allow some NoSQL people to come back and use Vitess for the fact that it gives you relational functionality with some trade-offs.
Yeah, definitely. That's some of the hope. So
only time will tell.
Yes.
Cool. All right. Actually, this is a good stopping point. The next set of slides, you can actually go through these examples yourself as homework. So maybe we can cover these faster next time. it basically tells you, throws a whole bunch of queries and how they should be handled by V3. The way you look at it is you look at these queries as queries generated by your app into a sharded database. And the way the homework for you is what should happen to each of these queries. How should this query be executed is the question that you kind of have to answer to yourself. So you can take a look at this, and then we can brainstorm about what should happen for each of these queries tomorrow.
Great. Thank you.
Sounds good. And so we'll meet tomorrow again, same place, same time.
Sounds good.
Yep.
All right.